Hello everyone, my name is Tiago. I'm a fourth year PhD candidate at CGO in France, and I'm here to present the work Seamless Compiler Integration of Variable Precision Floating Point Arithmetic. Floating point units are everywhere nowadays, from smartphones and GPUs to in data centers and even MRI scans. With what all of them have in common is that they use the IEEE standard to define the formats that are being used for floating point arithmetic. While these formats generally are very suitable for most of the applications, many applications have different needs. So for example, neural networks use bfloat 16 because they have a higher dynamic range in the exponent. Other applications such as linear solvers and body problems and other applications in mathematical physics, they benefit from non-high precision representations. So in those cases, accuracy is actually very important. Take a look at this example of the polybench applications covariance and Gram-Smith being compiled with 4 different types. We see that the accumulation of round-off errors in the output can be really high. So for example, for the Gram-Smith here, we see that IEEE 32 and 64 actually provide a really high round-off error at the output. So is the case for the covariance being compiled with dataset really huge. So in this case specifically, our goal is to make accuracy exploration very easy in order for us to explore what is the best trade-off between accuracy, speed, and energy. So precision control is actually a key feature for numerical analysts. The idea of exploring the trade-offs between accuracy and execution time and energy is actually really important. But how can one write applications in order to explore accuracy? Well, one of the ways we have to do that is through variable precision computing. The problem is that variable precision computing is not currently supported in compilers and languages nowadays. Either we need to resort to IEEE formats that have fixed sizes. So for example, IEEE 32 and 64, or we need to resort to libraries like MPFR and Boost, which are actually very slow and have no inherent compiler support. And in neither of those cases, we have a way to explore different floating point representations. So the real challenge behind this is to provide language and compiler support for variable precision computing so that we can provide access to the precision attribute, including ways to dynamically adjust it. And also, compiler support memory management is very important. There are different works in the state of the art that try to mimic variable precision computing. Mixed precision approach is one that combines IEEE formats for speed and energy efficiency. It has hardware support, but is still limiting on the number of types that we can use. Multi-precision libraries like MPFR and GMP offer high flexibility, but have no hardware support. And Flights from Anderson 2016 works with non-traditional formats. It has hardware support as well, but requires IEEE conversions, which means there's no support for high precision in any sort of way. So the main contribution of our work is a generalization of mixed precision to arbitrary or variable precision. We propose a C-type extension to represent variable precision floating point arithmetic that combines an LLVMIR extension to handle generic floating point types and backend code generators for software and hardware targets. This allows us to work with non-traditional formats. It has hardware and software support and is fully integrated with an industry-level compiler. The compiler flow that we actually follow is through LLVM. So I'm going to define and show you exactly what needed to be done in each one of these phases of the compiler. So starting from the front end, we propose a C-type extension to represent variable precision arithmetic. We do that by providing support for the VP-float keyword, which requires us to specify a series of attributes. One of them is the type, which actually tells us which is the type that's being used, what is the representation that you're going to use, an exponent information, a precision information, and a size information. So the type can be a UNO type, which was defined by Gustavo in 2017, or the MPFR type, but other types can also be added. Each one of the remaining attributes can either be integer literal, which means that we can define constants, and that makes us declarations of static types, or an identifier, which are the variables of the code, which makes the types with attributes that are only known at runtime. So two of the formats that we have are MPFR types and the Unum types. And for this MPFR type, what we do is we have LLVM transformation in the middle end that's going to change all the references from VP-float MPFR to MPFR. And there's no limitation to the value of the mantissa that we use. So the VP-float MPFR specifies an exponent and a mantissa. So these are the examples of a VP-float MPFR type being defined with 16 bits of exponent and 100 bits of mantissa. And this is the VAXP example, which shows that prec here is being used as the mantissa of alpha, pointer of x, and pointer of y. For the Unum types, we have a different reasoning. They requires us to specify an ESS and an FSS field that come from the Unum format header. We implement a simplified version of the ISA proposed by Boko, where ESS is between 1 and 4, and FSS is between 1 and 9. We also propose a size field that actually limits how ESS and FSS grow. So this is an example of an AXP function being implemented with a Unum type with 4 ESS, 6 FSS, and 8 bytes of size. And this is the GEMV function being implemented with FSS being the value of prec. Both of these types, VP-float, MPFR, and Unum, they can always be defined either as types with constant attributes, which means that attributes are known at compile time. They work very similar to regular floating point types. So they are easy to control the mantissa, the exponent, its size, and how to do memory allocation. And the values of literals can actually be set by adding the suffix v for VP-float Unum and y for VP-float MPFR. So this is one of the examples, just like I showed you before, of a declaration with constant attributes. And as well, we can define both of the types with variable attributes. So in this case, the floating point attributes are only known at runtime, and they can only be declared inside the functions. So it can be local variables, function parameters, or function returns. One of the first challenges we have with this is how can we provide literals for dynamically sized types? So the way we do it is through a fixed size representation in a maximum configuration. For Unum types, it's according to the maximum provided by the ISA, which means we have an exponent of 16 bits and a mantissa of 512 bits. And for the MPFR types, a maximum configuration means 16 bits of exponent and 240 bits of mantissa. A second major challenge is how memory is allocated for dynamically sized types. In this case, we take a similar approach to the variable length arrays in C. Just like we can see here in this function, the value of n is not known until runtime evaluation. So for each declaration of a dynamically sized type, we actually generate a call to the size of VP-float function that actually tells us how many bytes of memory needs to be allocated. So in this case, specifically of the for loop over here, alpha AX will be allocated in memory every time we go into the loop. So in this case, for every time we are going to call the size of VP-float function that tells us how many bytes need to be allocated. Types with variable attributes can either be parameters, local variables, or return values. And runtime attributes can be local variables, parameters, or global variables. And we implement runtime verification whenever possible so that to guarantee that the types are being formed properly. In terms of type conversions, comparison, and casting, we implement no implicit conversion, so it's up to the user to decide what is the conversion it needs to be done. In terms of the modification needed in the middle end, we added support for a new IR type system that is deeply integrated with LLVM. This allows us to use the classical optimizations and even profit from their transformations of code. The floating point attributes that are needed for each one of the types is implemented with the LLVM value objects, which can express instructions, constant function parameters, or global variables. And one important characteristic of our type system is that there is no def-use relation between these types and the values. That would require major modifications, and we opted not doing that way. So instead, what we do is values are tracked through separate lists, and each one of these values is marked with an intrinsic calls, which means that we are able to update them but not delete it. Additionally, we try to evaluate what are the transformation passes that needs to be updated or that cannot run for specific types. One of them is the loop idiom recognition, which essentially transforms a simple loop into a non-loop form. And in this case, we modified it for the dynamically sized types, and we actually disable it for the VP float MPFR due to having this pointer over here into the instruction of MPFR. We also updated inline to support this dynamically sized type or the type with runtime attributes. And in this case, what we do is we mutate the type to comply to the new inline function. In terms of the backend, we then provide support for two different backends, one for a software target and another one for the hardware target. So the first backend consists on a LLVMIR transformation pass that changes all references from VP-float MPFR to the real MPFR library. And because MPFR actually has a struct with a pointer, it requires us to treat and handle all the allocations and frees of the objects. Each one of the operations that is performed with the VP-float MPFR is actually changed in order to correspond to the right functions and operations with the MPFR library, just like we can see here in this picture. Compound types like class or structs that make use of the VP-float types are reconstructed as MPFR struct types. So is the case for the virtual tables that are all updated with new MPFR references. Although loop idiom recognition has been disabled, the compiler can still make use of memcopies and memmoves functions by using the C++ standard library. In this case, our code generator detects and calls a set of additional functions in order to provide full support for memcopies and memmoves. OpenMP Atomic also requires special treatment, as it's not possible to atomically update an MPFR variable due to the pointer reference in the struct. In our case, we implement our own compare and exchange through a dedicated mutex. So for the UNO backend, we use the RISC-V ISA extension for the UNO format that was proposed by Boko. It has multiple levels of precision for up to 512 bits, and it's a byte-aligned floating point value in memory. The values of ESS and FSS fields, the ones that I showed you before, are actually stored in status registers, and we can also set the values of the operating precision of the arithmetic operations and how many bytes are read and written in the memory. We also implement two UNO-specific passes. The first one consists of analyzing and configuring the values of ESS, FSS, the operating precision, and MBB, which actually tells us how many bytes in memory we need to read from or write to. And this is done according to the type information declared by the user and through the status registers that are inside the coprocessor. The second pass runs on dynamically sized types and aims at providing proper array address calculations for these types which have non-fixed sizes. So this is something that's not supported natively by LLVM. The first experiment that we did was to compare the VP-float MPFR with Boost multi-precision library, both of them generating MPFR code in Polybench suite and also in Rajaperf and with different configurations. This was artifact evaluated and reproduced. So in terms of the results that we got, this was done in a machine Intel Xeon with 8 cores and 16 hardware threads. And for the Polybench suite, we have a average speed up of 80% over Boost. And Rajaper sequential is 67% faster than Boost, while the parallel version had 7 times speed up over the Boost library for multi-precision. which was actually a very surprising result that we got. So how can we achieve this speed up? Well, first, because we have a tight integration with LLVM, and that allows us to have a better exploration of the classical optimizations inside the infrastructure. Our solution also scales much better than Boost in a multi-thread environment because we are able to reduce the number of memory accesses and cache misses as well. And many of the situations we have seen that Boost can transform many of the compute-bound kernels into memory-bound ones. And in our case, we're able to achieve much better performance than Boost in a multi-thread environment. The second experiment that we perform is VP-Float Univ versus VP-Float MPFR with the Polybench suite. And the idea is to compare a hardware support with a software support. This was done in a RISC-V Rocket processor connected to the Univ processor. So to summarize the speed up that we got when executing a hardware support in comparison to a software support, we have a speed up of more than 18 times when using O3 and more than 27 times when using O3 plus poly, which means that we're not only able to better explore the optimizations when using a hardware target, but we are also able to explore poly optimizer, which gives us much better performance than a baseline. Our last experiment consisted of a great exploration tool for precision awareness. The idea is to explore that with adaptive or very precision computing. And we do that with the conjugate gradient algorithm, which is an iterative solver for linear systems. In this case specifically, our concern is try to understand how the number of iterations vary according to the precision that we use. So we implement that in a precision generic conjugate gradient algorithm with the VP-Float MPFR. So we see here in the left graph that by increasing the number of bits in the algorithm, we can actually reduce the number of iterations. And this is also more or less true for the execution time, except that the execution time doesn't follow the exact same trend as the number of iterations. But we still, by augmenting the precision, we are able to reduce the execution time of the applications. We should point out that this experiment was done in a single run of the application without needing to recompile the code, which enables us to programmatically drive experiments with multi-precision configurations. And once more, we have 51% better performance than Boost. And we also outperformed the Julia version by more than 9 times. In conclusion, we propose a C-type system and IR and backend generators for very precision floating point arithmetic. We propose floating point representations with attributes that are known at compile time, but also those that are only known at runtime. This allows us to have high productivity and also high performance in order to explore different configuration of precisions. We also extend LLVM, and we are able to leverage most of the existing optimizations inside the infrastructure. We also propose and provide strong speedups for Polybench, Rajaperf in both software and hardware targets. Additionally, you can find more information about this work in the published paper. Thank you very much.